Welcome back, Design Junkies, to Mechanical Engineering Made Simple. If the podcast brings you value, help support the show with a like, a follow, or leave a comment below. So, imagine this scenario for a second. You are the lead engineer on a project, right?
Okay.
And you have just spent, I don't know, the last 3 years of your life and upwards of 50 million bucks designing this state-of-the-art axial turbine.
Oh, man. High stakes.
Right, high stakes. And, the math checked out, the CAD models looked completely pristine. So you spin this massive piece of machinery up to operating speed for the very first time, and within like 3 seconds before anyone can even hit the emergency stop button, it just violently tears itself to shreds.
Yeah, just complete catastrophic failure.
Exactly. The casing shatters, the blades turn into literal shrapnel, and here's the really crazy part. It wasn't hit by a foreign object, it didn't overheat, it literally vibrated itself to death. Like, it used its own energy against itself.
It is, it's a heartbreaking scenario, but it's one that is entirely too common in the field, unfortunately. Destructive vibration really is like the invisible gremlin of mechanical design.
Yeah, and I want to speak directly to you listening right now, because whether you are designing a massive jet engine or, a simple household hair clipper, or even a long, boring bar for a lathe and a machine shop vibrations, are these invisible forces that can completely tear your hard work apart.
They're absolutely relentless.
They really are. So our mission today in this deep dive is to unpack a massive stack of mechanical engineering source material to tackle this exact pain point. We are going to break down the biggest real-world issues that engineers run into, call out the common misconceptions that keep screwing up designs, and then walk through a step-by-step approach to actually optimizing your systems.
And we mean out in the real world, right? In practice, not just on a piece of idealized paper.
Exactly. Because okay, let's unpack this. I think that first misconception is where a lot of the standard textbook theory tends to leave you hanging, right?
Oh, absolutely. The paper model, sitting in a frictionless vacuum, it looks perfect. But the physical prototype sitting on the test stand shakes itself to pieces. It requires a really fundamental shift in how we understand the physics of motion.
Let's start right there, actually, with that first major misconception, because I think a lot of us, when we see a machine violently shaking or hear it screaming, we immediately diagnose it as resonance.
Right.
We think, oh, the operating speed must just be matching the natural frequency of the frame. It's like the go-to culprit for everybody.
It's the most common trap. And it's because resonance is what we are taught first in introductory dynamics. It makes intuitive sense to us.
Yeah.
In a forced resonance scenario, you have an external stimulus. So think of an unbalance in a rotating shaft. Maybe a small chunk of metal is just missing on one side. As the rotational speed of the machine approaches the inherent natural frequency of the entire system, the vibration amplitude peaks.
Like pushing a kid on a swing at the exact right moment so they go higher and higher.
Yeah, that's a great baseline analogy. But here is the critical defining characteristic of forced resonance that engineers always seem to forget. It peaks in a very narrow band of RPM.
Okay, a narrow band.
Right. So if you have the horsepower to push the machine past that critical speed, the vibration amplitude actually drops back off. It decreases.
Let me make sure I'm visualizing this right. It's like a spike on a graph, essentially.
Exactly.
You hit the bad speed, the machine gets super loud, the whole floor is shaking. But if you just keep accelerating, push through that danger zone, you get to a smooth operating speed on the other side.
Yes, exactly. But what our source material highlights today is a completely different and, frankly, far more terrifying beast. It's known as self-excited vibration.
Self-excited, that just sounds bad.
It is. This encompasses phenomena known as whirling or whipping in rotating machinery. And the behavior is, well, it's fundamentally different. With self-excited vibration, there is no narrow band. Once a machine hits a specific onset speed, the vibration suddenly increases, and it absolutely does not drop off if you speed up. It stays violent, and usually it gets exponentially worse as the speed increases.
Wait, really? So you can't just power through it? It just keeps feeding on itself?
Until the machine yields or it just catastrophically fails, yeah. And the other vital difference involves how we actually try to fix it.
Rate to mitigation.
Yeah. In a forced resonance situation, if you add damping to the system, say you bolt on a viscous shock absorber or maybe add a heavy rubber isolation mount, you can significantly reduce that peak amplitude at the critical speed.
Because the damping is basically pulling the energy out.
Exactly. But with self-excited vibration, Adding damping might just delay the onset. It might force you to reach a slightly higher RPM before the chaos starts.
But once you hit that new, higher RPM,
The damping will not materially affect or reduce the peak amplitude at all. The machine will still tear itself apart, just at a higher speed. You haven't actually solved the problem. You've just, moved the explosion to a different point on the tachometer.
that is genuinely terrifying from a design perspective, because you think you fixed it, right? You sign off on the safety report because, hey, you added a heavy-duty shock absorber, but you've actually just created this false sense of security.
Yeah, it's a huge trap.
Why does it act like that, though? Like, what is the actual physics behind a machine feeding itself energy?
Well, the text uses a really fascinating mathematical concept to explain this. Think of the classic vibration equation as like a balancing act. You have three main physical properties at play.
Okay, let's break them down.
First, you have the mass of the object, which dictates its acceleration. You have the stiffness of the spring, which fights the displacement. And you have the friction, or the damping coefficient, which fights the velocity.
Right, the classic spring mass damper system. Mass, stiffness,
Right.
friction.
Exactly.
Yeah.
And in the math, it's written as m times x double dot plus c times x dot plus k times x equals 0.
The classic differential equation.
Yeah. For that system to be stable and not shake itself to pieces, the damping term, that C value, has to be doing its job. It has to be pulling kinetic energy out of the system and turning it into heat. Mathematically, the amplitudes of the vibration decay over time.
Right, they get smaller and smaller until it stops.
But in self-excited vibration, the system develops what the math refers to as negative damping.
Negative damping, I mean, that sounds like an oxymoron. How can friction be negative?
It's a mathematical way of describing a physical reality where the force meant to slow the system down basically flips its sign. So instead of C being positive, you get a term that looks like negative C plus some constant times x squared.
Oh, wow.
Yeah. Instead of bleeding energy out of the system, it's injecting kinetic energy back into the motion. The equation essentially demands that the amplitude grows exponentially because the system is actively extracting energy from its own rotation to feed the vibration.
Okay, let's go back to the playground swing analogy for a second. If positive damping is like air resistance and the friction in the chains slowing the swing down over time,
Right.
what is negative damping? Is it like the swing has a hidden motor on it?
It's more like the system is acting like a person standing behind the swing, pushing you higher and higher with every single pass.
Okay, that makes sense.
And in rotating machinery, that person pushing the swing is typically a tangential force.
Tangential meaning pushing from the side.
Yes. The whirling is predicated on the existence of some physical phenomenon that induces a force normal or perpendicular to the radial deflection of the shaft.
Okay, I'm trying to picture this.
Imagine a heavy steel shaft spinning. It bends slightly outward from the center axis due to gravity, or maybe just some tiny microscopic imperfection in the metal.
Sure.
Suddenly, a force appears that pushes it sideways, perpendicular to that bend, right in the direction of rotation. This lateral push opposes the inherent damping of the metal and pushes the shaft into a forward whirl. It starts orbiting its own center.
Okay, I understand the concept of the invisible person pushing the swing sideways, but what are the actual physical mechanisms? Like, how does a chunk of spinning steel accidentally generate a sideways force out of nowhere?
It's not out of nowhere, and that is exactly where engineers get tripped up. The sources detail several specific traps that create this exact scenario. Let's look at the first one, which is called hysteretic whirl.
Hysteretic whirl.
Okay, this comes from internal friction within the rotating shaft itself.
Internal friction, like the actual metal molecules rubbing together inside the solid steel.
Basically, yes. Or, even more commonly in large machines, it's friction at the interfaces of joints, like shrink fits, collars, or bolted elements stacked on a rotor. Let's visualize the bending shaft again. When it deflects, the side on the outside of the curve stretches its in tension. The side on the inside of the curve squishes together its in compression.
Makes total sense, like bending a raw piece of spaghetti.
Right.
Perfect analogy. In a perfect, purely elastic world, the line of zero stress, the exact center, where it's neither stretching nor compressing, lines up perfectly with the geometric center of the bend.
Right.
The restoring force, the strength of the steel trying to straighten itself out, points straight back toward the center line.
Meaning the shaft just wants to snap back to being perfectly straight, so it's pulling straight inward.
Exactly. But we don't live in a perfectly elastic world. Because of hysteresis, that internal friction of the material grains resisting motion, there is a phase shift.
Phase shift?
Yeah. The stress takes a tiny fraction of a millisecond to actually develop as the shaft fibers rotate through the peak strain.
Oh, I see. Because it's spinning while it's bent. The part of the metal that is on the outside of the curve is constantly changing as the shaft rotates?
You've got it. And because of this delay, the physical location of the maximum stress gets dragged slightly forward in the direction of rotation. The neutral stress axis gets displaced in angle from the actual geometric bend. So the resultant elastic restoring force doesn't point straight back to the center anymore. Because of that delay, the force vector tilts. It now has a tangential component.
A tangential component.
Yeah.
Which means the steel's own attempt to straighten itself out is actually pushing itself sideways. That's the invisible person on the playground swing.
Yes. And because this force pushes the shaft sideways in the direction of rotation, it increases the centrifugal force, which bends the shaft even more outward, which creates more internal stress, which creates an even larger tangential push.
Wow.
It is a runaway feedback loop powered entirely by the friction inside the metal.
That is absolutely wild. You always think friction stabilizes things, but here internal friction is what literally destroys the machine. Now, the source material also mentioned something about fluids causing this, right?
Yes, that is trap number 2, fluid trapped in the rotor. This is a massive headache in centrifuge applications, jet engine drums, or really any hollow rotor.
I'm picturing like an unbalanced washing machine on the spin cycle. Is it like that?
It's a very similar principle. If you have liquid trapped in a hollow cavity and the shaft deflects slightly from the center axis, what happens to the fluid?
Centrifugal force throws all the fluid to the outside of the bend?
Exactly. The fluid pools on the outermost edge of the curve. And this acts as a massive unbalance that dynamically moves with the deflection. It adds an eccentric mass that pulls the shaft further out, creating a forward whirl that feeds on itself.
That seems like an absolute nightmare to try and balance out with counterweights because the fluid is constantly moving around. Is there a fix for that, or do you just have to hope oil doesn't ever leak into your hollow shaft?
The practical fix, assuming the fluid isn't fundamental to the machine's actual function, is remarkably simple and elegant. You just provide drain holes at the absolute outermost radius of all the hollow cavities.
Seriously. Just drill a hole and let centrifugal force throw the fluid out of the machine.
Essentially, yes. Give the fluid a way to continuously escape so it can never pool up and drive a whirl in the first place. It's a design feature you have to anticipate rather than a problem you can tune out later.
A simple drain hole saves a $50 million, well, a $50 million buck turbine. I love that so much. What is the next trap?
Trap number 3 is highly counterintuitive. It is called fluid bearing whip. This happens in fluid-filled clearances, specifically journal bearings or seals.
Let's define a journal bearing for anyone not steeped in engine design. We aren't talking about tiny steel ball bearings here.
No, not at all. A journal bearing is basically a smooth metal shaft spinning inside a slightly larger smooth metal sleeve.
Wait.
They don't actually touch.
Right.
Instead, oil is pumped into the tiny gap between them, and the spinning shaft basically hydroplanes on a microscopic film of highly pressurized oil.
Okay, so the shaft is literally floating on liquid. How does that cause a destructive whirl?
It comes down to fluid dynamics. The viscous oil trapped in that tiny clearance gets dragged around by the rotating shaft. The oil touching the stationary outer sleeve isn't moving, right?
Right.
But the oil touching the spinning inner shaft is moving at the shaft's surface speed. So the average speed of the oil circulating in that gap is roughly half the shaft's surface speed.
Makes sense. It's like a swirling vortex of oil.
Now, if the shaft deflects radially, let's say it wiggles slightly off-center, it squeezes the fluid on one side of the bearing, creates a really tight bottleneck.
Okay, so the swirling oil suddenly has to jam its way through a much tighter space.
Correct. And because of viscous losses, as the fluid forces its way through that tight squeeze, the pressure profile changes dramatically. The pressure on the upstream side of that tight clearance becomes significantly higher than the pressure on the downstream side after it squeezes through.
Which creates an asymmetric pressure profile all the way around the shaft.
Exactly. You have high pressure pushing on one side of the wiggle and low pressure on the other. That asymmetric pressure results in a net tangential force pushing the shaft forward into a whirl.
Oh, man.
If this fluid force exceeds the inherent damping of the heavy metal bearing block, the whirl starts. The shaft gets pushed sideways, the centrifugal force increases, the clearance closes even further, the pressure differential spikes even higher, and the machine rapidly destroys itself.
It just spirals completely out of control. It's literally using its own lubricating oil as a weapon against itself.
Yeah.
Does this same asymmetric pressure thing happen with air, like in the turbine example I gave at the start of the deep dive?
Yes, it absolutely does. And that leads directly to trap number 4, the turbomachinery tip clearance effect.
Hmm.
This is a massive issue in power generation and aviation.
Okay.
In an actual turbine, you have hundreds of blades spinning very close to a stationary outer casing. The gap between the spinning blade tips and the stationary wall is the tip clearance.
And engineers want that gap to be as microscopic as physically possible, right? Because any hot gas that slips through that gap isn't pushing the blade, so it's basically wasted energy.
Exactly. It's all about thermodynamic efficiency. But if the massive rotor deflects radially, say it sags or bends just a fraction of a millimeter, the blade tip clearance closes up on one side of the engine and opens up 180 degrees away on the opposite side.
Meaning the blades that are scraping dangerously close to the wall on the tight side are suddenly way more efficient at extracting work from the gas flow than the blades on the wide open side.
You nailed the physics. That localized increase in efficiency means a much greater local blade force. The tight side is extracting more energy and experiencing more thrust than the loose side.
Wow.
That imbalance of work extraction creates a net tangential force driving a forward whirl.
It's almost like the machine is being punished for being too efficient on one side. The gas literally pushes it further off center.
And finally, we have trap number 5, propeller whirl. This is distinct from the others because it involves gyroscopic forces and aerodynamics. This happens when the rotating shaft has a slight angular deflection, a tilt, rather than just a parallel offset.
Give me a visual for this one.
Okay, imagine a large turboprop airplane flying straight forward. The propeller is a giant disc spinning at the front. Now imagine the engine mounts flex slightly and the entire spinning propeller disc tilts slightly upward.
Okay, so it's looking up at a slight angle relative to the airflow.
Because of that tilt, the angle between the plane's forward approach velocity and the propeller blade's rotational velocity changes. For a blade swinging downward on the right side of the engine, it hits the oncoming air at a slightly different angle of attack than a blade swinging upward on the left side of the engine.
Right, because one blade is rotating into the tilted airflow and the other is rotating away from it.
Yeah. Exactly. This creates a cyclical change in the aerodynamic load magnitude and direction for every single blade as it completes a rotation. The cumulative effect of these changing aerodynamic forces creates a massive destabilizing moment on the shaft.
Uh-oh.
If the airspeed of the plane is high enough, this destabilizing moment overcomes the structural damping of the engine mounts, resulting in a destructive conical whirling of the entire engine system.
So the engine basically starts tracing a giant cone shape in the air until it just rips off the wing.
It has happened historically, yes.
Yeah.
And uniquely, due to the gyroscopic dynamics, this propeller whirl is generally counter to the shaft rotation direction. It induces a backward whirl, whereas the other fluid and friction traps induce a forward whirl.
This is, I mean, it's a lot to take in. But the overarching lesson here seems really critical. You can't just look at a vibrating machine, slap a giant rubber damper on it, and assume you fixed it. You have to be a forensic engineer. You have to understand if the vibration energy is coming from an external bump in the road, or if the system is literally generating the destructive force itself through its own rotation, friction, or fluid dynamics.
Recognizing the fundamental difference between forced resonance and self-excited instability is step 1 in saving your design. If you misdiagnose a self-excited whirl as a forced resonance, your mitigation attempts will almost certainly fail.
Okay, let's pivot to the second major misconception from our source material, because this one moves away from the physical traps and into the realm of math and modeling. There is a huge trap here regarding what the text calls lumped parameters.
Ah, the lumped parameter model. It is how almost every mechanical engineer is taught to think about vibration in their undergraduate dynamics courses.
Right.
It's a simplification tool. You take a highly complex physical machine and you abstract it into 2 completely separate concepts: a rigid, infinitely stiff block representing all the mass, and a perfectly weightless, idealized spring representing all the flexibility.
The classic block sliding back and forth on a frictionless surface attached to a squiggly line on the chalkboard. We've all seen it.
We've all drawn it 1,000 times. And for very simple systems, or for rough first-order approximations, it works. It gives you a mathematical model with a finite number of degrees of freedom.
Okay.
If you have 1 block and 1 spring, you have 1 degree of freedom, which means the math yields exactly 1 natural frequency. If you model a car suspension as 4 distinct blocks on 4 distinct springs, you have 4 degrees of freedom, and 4 natural frequencies.
It's clean, it's solvable on a single piece of notebook paper. But, the real world doesn't look like an idealized block and a weightless spring.
It doesn't. In physical reality, every elastic member has mass, and every mass has some degree of elasticity. Real systems have what we call distributed mass and distributed elasticity.
Let's ground that a bit. What's a good example of distributed mass?
Think of a simple diving board or a uniform steel beam used in construction. The mass of the diving board isn't concentrated entirely at the tip where the person stands, right?
Right.
The mass is distributed continuously along every single inch of its length. And the flexibility isn't just at the base. The board flexes continuously along its entire length.
So if we abandon the simplified block and spring model, how many degrees of freedom does a real physical diving board actually have?
Because the mass and flexibility are continuous down to the molecular level, it effectively has an infinite number of degrees of freedom.
Infinite.
Yes. To completely define the mathematical configuration of a vibrating beam at any given millisecond, you would theoretically need to know the exact spatial deflection of every single infinitely small section along its entire length. And here is the terrifying part for a math model. Because it has infinite degrees of freedom, it possesses an infinite number of natural frequencies.
Here's where it gets really interesting. Because as a working engineer in the modern world, you can't exactly plug infinity into your CAD software or your math model and expect to hit your Friday deadline.
No, you definitely cannot.
Solving the partial differential equations required to map infinite degrees of freedom across a complex 3D shape is an absolute nightmare.
It is more than a nightmare in many cases. It's analytically impossible. The math gets incredibly dense, incredibly fast. While exact classical solutions exist for a few very simple academic configurations, like a perfectly uniform beam with perfectly pinned ends, most real-world designs, like a tapered turbine blade or an irregularly shaped engine block, are just far too complex for an exact partial differential equation solution.
So engineers are basically caught between a rock and a hard place. They either oversimplify with lumped parameters and get a bad result that leads to a broken prototype, or they drown in partial differential equations trying to solve for infinity.
Right.
But the source text gives us a hack, a step-by-step practical approach to bypass the nightmare math but still get highly accurate results for continuous distributed systems. It's called Rayleigh's method. I want to break this down slowly. How does it work?
Rayleigh's method is an incredibly elegant application of the conservation of energy. It is brilliant in its simplicity because it sidesteps the partial differential equations entirely. It's primarily used to find the fundamental natural frequency, the lowest and usually most dangerous vibration frequency of a distributed system.
Okay, let's walk through it. Say I have a complex steel beam. What is step one?
Step 1 is to assume a deflection shape for your vibrating body. You don't need to know the exact, mathematically perfect dynamic shape it will take while vibrating. You just need to guess a realistic shape.
Wait, just guess. That seems super unscientific.
It's an educated guess. Very often, engineers will just calculate the static deflection curve. Imagine the beam is bolted to the wall. What shape does it take if you just let gravity pull on it? It sags.
Okay, yeah.
You calculate that static sag curve, which is basic structural mechanics, and you use that curve as your assumed dynamic shape.
Okay, so I assume a shape. I have a mathematical curve mapped out. What is step two?
Step 2 is to calculate the maximum potential energy, or the strain energy, of the system. Let's visualize the beam vibrating up and down. At the absolute peak of its upward swing, for a microscopic fraction of a split second, it is completely motionless before it reverses direction and snaps back down.
Right. It reaches the top of the arc, velocity hits exactly 0, and it changes direction.
Since velocity is 0 at that exact instant, the kinetic energy of the entire system is 0. Where did all the energy go? It is all stored as elastic strain energy in the bending of the metal beam. It's wound up like a spring.
Okay, I follow that.
You calculate the strain energy using your assumed deflection shape from step 1. For a beam, this involves a relatively simple algebraic integration of the square of the curvature along the length multiplied by the bending stiffness of the material. We'll call this maximum calculated strain energy, V.
Okay, we've paused time at the peak of the bend to measure the potential energy, V. But to use the conservation of energy, we need the kinetic side of the equation.
Yeah.
Where do we measure that?
We measure the kinetic energy at the exact opposite point in the vibration cycle. We look at the moment when the beam is snapping back and passes exactly through its neutral, perfectly flat equilibrium position.
At that exact moment, it's not bent at all. It's completely straight.
Exactly. And because it isn't bent, the elastic strain energy is 0. All the stored potential energy has been completely converted into velocity. All the energy is now kinetic.
How do we calculate that?
You calculate the kinetic energy by integrating the mass distribution along the beam multiplied by the square of the velocity profile. Since we are assuming simple harmonic motion, a smooth sinusoidal waves, the velocity at any point is simply the deflection shape we guessed in step 1, multiplied by the natural frequency, which we represent with the Greek letter omega n. We'll call this maximum kinetic energy T.
So we have an equation for maximum potential energy, V, and an equation for maximum kinetic energy, T. I assume step 4 is where we smash them together.
That's the magic. Step 4 relies on the inviolable law that energy is conserved. Assuming there is no damping sucking energy out of the void, the maximum strain energy V must exactly equal the maximum kinetic energy T. You simply set the equation for V equal to the equation for T.
And because the velocity term in our kinetic energy calculation contained the natural frequency, omega n squared, we now have an algebraic equation where omega n is the only unknown variable.
Precisely. You factor it out and solve for it using basic high school algebra.
That is incredibly slick. You bypass all the infinite differential equations and just balance the energy accounts to find the frequency. But I have to push back on step 1. You said to assume a shape. What if I guess wrong?
That's the common fear.
If I use a static gravity sag for a beam that actually vibrates in a weird twisting motion, isn't my answer completely useless? Does the whole energy trick just fall apart?
That is the most beautiful, profound part of Rayleigh's method and why it is so beloved by engineers. If you somehow guess the absolute, mathematically perfect dynamic mode shape in step 1, your energy balance will calculate the exact true natural frequency. But if you guess a slightly wrong shape, which you almost certainly will because you're human, your answer is not useless. It is bounded.
Bounded to how?
The source text highlights a fundamental mathematical truth about elasticity. The frequency found using any assumed shape except the absolute correct one will always be higher than the true actual frequency. It will never be lower.
Wait, always higher. Why does a wrong guess always drive the frequency up?
Think about it physically. The true, mathematically perfect natural mode shape is the path of least resistance for that specific structure to vibrate. It represents the absolute most flexible, unconstrained way the physical mass can move.
Okay, nature finds the easiest path.
When you assume a slightly different shape, say, you force the math to pretend the beam bends like a parabola instead of a complex sine wave, you are essentially implying a mathematical constraint. You are mathematically forcing the beam to move in an unnatural way.
And what does constraint do to a physical system?
Any artificial constraint adds artificial stiffness to the system. And in the world of vibration, higher stiffness always equates to a higher calculated frequency.
Oh, wow. I'm literally getting chills. So the math inherently penalizes bad guesses by driving the frequency up. The worse your guess, the stiffer the artificial model and the higher the fake frequency.
Exactly. So in real-world practice, an engineer doesn't just guess once. They assume 2 or 3 different reasonable deflection shapes. They run the quick algebraic Rayleigh calculation for each one and simply look at the resulting frequencies. Because you mathematically know that a wrong guess always yields a higher frequency, you just pick the lowest number.
That makes total sense.
The lowest computed frequency out of all your attempts is absolutely guaranteed to be the most accurate approximation of the real fundamental frequency.
That is such a powerful, elegant tool. It changes the entire engineering mindset. You shift from, I need to solve an impossible infinite equation to, I just need to make 3 agitated guesses, balance the energy, and let the laws of physics sort out the winner.
If we connect this to the bigger picture, it shows that deeply complex distributed mass problems can be managed with relatively simple algebra as long as you deeply understand the underlying physical realities of strain and kinetic energy.
Okay, this is a perfect transition. We've talked extensively about how machines generate their own destructive vibrations through traps like hysteretic whirl and asymmetric fluid pressure, and we just covered how to properly calculate the natural frequencies of complex, continuous structures so we actually know where the resonant danger zones are. Now I want to transition from playing detective to playing mechanic. We need to actually fix the problem.
The mitigation phase. This is where engineering becomes an art form.
Right. Let's set up a scenario. Say I am designing a machine. Despite all my best efforts to stiffen the frame, or lighten the mass, or use Rayleigh's method to analyze it, the physical reality is that it is still shaking itself apart at a constant specific frequency.
Okay, pretty common.
Maybe it's a massive industrial compressor. I can't change the operating speed because the factory needs a specific airflow, and I can't redesign the whole chassis because it's already cast in iron. The vibration is there, it's destructive, and I'm stuck with it. How do I stop it?
This is where we introduce one of the most clever devices in mechanical engineering, the dynamic vibration absorber.
A dynamic vibration absorber. Let's unpack the mechanics of this. What is it?
At its conceptual core, an undamped dynamic vibration absorber is remarkably simple. It's an auxiliary mass attached to your primary vibrating machine via a spring.
Wait. I'm trying to stop my massive machine from shaking, and your solution is to bolt a smaller bouncing mass on a spring onto the side of it. How does adding more bouncing, rattling parts stop the bouncing? That sounds completely counterintuitive.
It does seem counterintuitive until you look at the force vectors. It relies on the concept of equivalent mass. When you attach this smaller auxiliary mass spring system to the main machine, it doesn't just bounce passively, it reacts back against the primary machine. The force it exerts backward depends on its own mass, its spring stiffness, and the specific frequency at which the main machine is shaking it.
Okay, so it's fighting back.
If you do the math, and you tune the auxiliary mass in spring so that their own independent, isolated natural frequency perfectly matches the troublesome excitation frequency of the main machine, something mathematically profound happens. At that specific frequency, the equivalent mass of the auxiliary system essentially becomes infinite at the point of attachment.
Infinite mass. We're back to infinity. What does that mean physically?
Think about Newton's second law. Force equals mass times acceleration. If you have a finite vibrating force trying to move an object that mathematically behaves as if it has infinite mass, the resulting displacement is zero.
Because you can't push a mountain.
Precisely. The auxiliary mass system starts bouncing wildly, but in doing so, it generates a reaction force through its spring that is exactly equal and exactly opposite to the disturbing force acting on the main machine. It completely cancels it out phase for phase. By doing this, it enforces what we call a node, a point of absolute zero motion, right at the physical point where the absorber is bolted on.
So the main machine literally stops moving. All the vibrational energy is sucked out of the heavy iron casting and gets trapped in this little auxiliary mass, bouncing its heart out on a spring. Let's ground this with a real-world example from the sources because it sounds like magic. The text talks about an electric hair clipper.
Yes, the classic barbershop hair clipper.
Yeah.
Inside the casing of that tool, you have an electromagnetic mechanism driving a set of steel cutter blades rapidly back and forth. Let's say it operates on standard North American alternating current, which cycles at 60 Hz. Because the magnet pulls in both directions of the AC wave, the mechanism cycles 120 times a second. The blades oscillate at exactly 120 Hz.
I've had a personal experience with this concept, actually. When I was in my 20s, I bought a super cheap discount bin palm sander to refinish a dining table. That thing didn't have any vibration mitigation. The heavy internal motor was just slamming back and forth. After 20 minutes of holding it, my hand went completely numb.
Oh yeah, standard.
The vibration was so intense it felt like my bones were buzzing, and my fingers tingled for 2 days afterward. It's a massive, unbalanced inertial force.
That is exactly the problem. If a manufacturer just bolted the cutting blades or the sanding pad to a plastic handle, it would cause severe user fatigue or even nerve damage over time. To fix this, good engineers design a dynamic vibration absorber and hide it inside the casing.
How do they tune it?
They calculate the exact unbalanced inertial force generated by the blades moving at 120 Hz. Then, they design a small auxiliary mass, maybe just a chunk of lead or steel and a specific spring, and they mount it inside the handle of the clipper. They meticulously tune the stiffness of that little internal spring and the weight of that little mass so that its own natural bouncing frequency is exactly 120 Hz.
And when the barber turns the clipper on,
The main electromagnetic blade starts shaking at 120 Hz. That vibration immediately transfers through the chassis to the handle. The handle vibrates, which immediately excites the little absorber mass. The absorber mass starts bouncing violently on its spring, but it naturally falls completely out of phase with the blades. It enforces a node right at the handle casing.
So if you possessed X-ray vision and looked inside the hair clipper while it was running,
You would see the cutting blades at the top thrashing left and right, and you would see the internal absorber mass in the handle thrashing violently right and left. The internal mass is going crazy, absorbing all the kinetic energy. But the outer plastic casing, the part the barber's hand is actually touching, is the enforced node. It feels essentially zero vibration. It feels perfectly still.
that is an incredibly elegant, almost beautiful design solution. You don't try to rigidly brace the blades, you just give the vibration a decoy to play with. But as much as I love that, the sources issue a pretty severe warning about this technique, right? It's not a universal silver bullet.
It is definitely not a silver bullet. And this brings us to the severe danger of perfect tuning. An undamped absorber works miraculously well, but only at the exact frequency it is tuned for. By bolting an auxiliary mass and spring to your system, you have changed the fundamental nature of the machine. You have increased the total number of degrees of freedom.
Oh, right, because we went from one mass spring system to two connected mass spring systems.
Exactly. And remember our rule from earlier, the number of natural frequencies always equals the number of degrees of freedom. So you have brilliantly eliminated the vibration at your specific target frequency, say 120 hertz, but you have inadvertently introduced two entirely new resonant frequencies into the overall system, one lower than 120 hertz and one higher.
Wait, you fixed one landmine but planted two more, so if the machine speeds up or slows down, it's going to hit these new resonances.
That is the exact danger. For a hair clipper plugged into a wall outlet, the frequency is locked at an absolute constant 120 hertz by the municipal power grid, so it's perfectly safe. The speed never changes. But imagine a massive industrial exhaust fan or a turbine pump that needs to spool up from a dead stop to a high operating speed.
Okay, I hit the green button, the motor starts whining, RPMs are climbing.
As it accelerates, the rotational frequency is going to cross that lower, newly created resonant frequency long before it ever reaches the smooth, tuned operating point. And because this is an undamped system, there's no friction to pull energy out. The vibration amplitude at that new, lower resonance will theoretically shoot to infinity.
So the giant industrial fan will literally shake itself off its concrete mounts and explode while it's still just warming up.
Yes, the undamped absorber will destroy the machine before it ever has a chance to do its job.
Okay, so if the excitation frequency fluctuates even a little bit, or if the machine has to spool up and down, a perfectly tuned, undamped absorber is actually a massive liability. So how do we fix the fix? How do we use the equivalent mass trick without planting the two landmines?
This leads to the necessity of damped auxiliary masses. We have to introduce a shock absorber, a viscous damper, maybe a piston pushing fluid through an orifice in parallel with the tuning spring of our auxiliary mass.
I have to challenge that. We just established that the magic of the absorber is that it bounces freely and perfectly out of phase to create infinite equivalent mass. If I put a thick, gooey damper on my auxiliary mass, it can't bounce around freely anymore. It's restricted. Doesn't adding friction ruin the exact node we just enforced?
You are exactly right. It does ruin it. Adding damping means the absorber is no longer 100% effective at the target frequency. The infinite mass effect is broken. The main machine will no longer be perfectly still. It will move a little bit.
Oh, why do it?
Because engineering is about managing trade-offs. The trade-off is that while you lose perfect stillness at the operating speed, the viscous damper now absorbs kinetic energy when the machine hits those two dangerous new resonant peaks during spool-up. It pulls their explosive amplitudes down to a safe, manageable physical level. It shifts the design from perfect fragile cancellation at one specific speed to robust, acceptable vibration control across a wide range of variable speeds.
Okay, I see. It's a compromise. You accept a tiny bit of vibration at the normal speed so the machine doesn't detonate when you turn it on or off.
It is a classic optimization problem. And the source text walks through a very specific, historically significant, step-by-step mathematical optimization of this damping. This is where mechanical engineering shifts from trial and error to an art form backed by calculus.
Walk me through it. How do we mathematically optimize the goo in the shock absorber?
Let's visualize a graph. We plot the response curve of the primary machine fitted with a damped absorber. The horizontal axis is the operating frequency, how fast the machine is spinning. The vertical axis is the vibration amplitude, how violently it is shaking. Because of our absorber, we know this graph will have two distinct mountain peaks representing those two new resonant frequencies.
Great, the two landmines we planted. A lower peak and a higher peak.
Now, imagine you are the engineer, and you have a dial that controls the viscosity of the damping fluid. If you turn the dial to row damping, you get two infinitely high, sharp spikes. If you turn the dial to infinite solid damping, basically welding the mass in place, you get one giant spike right in the middle because you've reverted to a single mass system.
Okay, so turning the dial changes the shape of the mountain range.
But the text points out a mathematical certainty that is almost magical. No matter what damping ratio you dial in, from 0 to infinity, all possible response curves on that graph will pass through two specific invariant points.
2 points that never move, no matter what you do to the friction.
Yes. The text calls them fixed points A and B. Their locations on the graph depend only on the masses and the spring stiffnesses involved. They are completely independent of the damping fluid.
So they act as pivot points for the curves.
Exactly. So the optimization process is a two-step balancing act to manipulate the mountain range around these two unmoving fixed points.
What's optimization step one?
Step 1 is tuning the spring. You adjust the tuning parameter, which means physically changing the stiffness of the auxiliary spring relative to the main system. When you change the spring, you move the fixed points. Your goal is to adjust the stiffness until the vertical amplitude at fixed point A is exactly equal to the vertical amplitude at fixed point B.
Okay, so I'm tweaking the metal spring until the two unmoving points are perfectly level with each other horizontally on the graph. I've leveled the playing field. What's step two?
Step 2 is the damping optimization. Now, you reach for your dial of fluid viscosity. You calculate and apply the absolute optimal amount of viscous damping to make the highest crests of the two mountain peaks occur exactly at or very close to those leveled fixed points A and B.
So by turning the dial, I'm squashing the two resonant spikes down until they basically form a flat plateau between point A and point B.
Exactly. You flatten the curve. The goal is to make the response curve as flat as possible as it passes between A and B, minimizing the maximum peak amplitude across all possible frequencies.
That is incredible. It shifts the design from just wildly guessing at oil thicknesses in a lab to a precise, mathematically guaranteed balancing act. You use calculus to find the exact point where the mountain range becomes a flat mesa.
It ensures that no matter what speed the machine runs at, from startup to redline, the worst-case vibration will never exceed that flat plateau level.
Okay, but this raises a really important real-world question. This flat plateau strategy works great for a fan or a pump that has to spool up and then sit at a constant speed. But what if the excitation frequency isn't just fluctuating a little bit around a target? What if I'm designing an internal combustion engine, like an automobile engine, where the RPM constantly and dramatically changes? A car goes from 1,000 RPM at a stoplight to 6,000 RPM merging on the highway over and over again.
Yeah.
A fixed frequency spring absorber, even a beautifully damped one, isn't going to cover a range that huge, right?
That is completely correct. For highly variable speed systems like internal combustion engines or marine diesels, the disturbing force isn't tied to a constant frequency in hertz. It is tied directly to the rotational speed. The excitation is a multiple of the RPM. In engine design, we call these orders of vibration.
Orders of vibration. Let's define that carefully for the listener.
Let's take a standard four-stroke, four-cylinder car engine. The main firing pulses the explosions in the cylinders happen twice per revolution of the crankshaft. So the primary excitation is the second order.
2 booms per spin.
Right. But depending on the exact geometry of the crankshaft, the connecting rods, and the fluctuating gas pressures in the cylinders, you might mathematically discover severe torsional vibration twisting of the metal shaft at a fractional order, say the 4.5 order.
Meaning the destructive twisting torque cycles 4.5 times for every single 360-degree revolution of the crank.
Yes. Now do the math on the frequency. If the engine is idling at 1,000 RPM, the 4.5 order is hitting the crankshaft at 4,500 cycles per minute.
But if I stomp on the gas and the engine revs to 5,000 RPM, the exact same 4.5 order is now hitting at 22,500 cycles per minute.
Exactly. The frequency you need to absorb is a wildly moving target. It scales linearly with engine speed.
So how on earth do you tune a steel spring to a moving target? A spring has a constant stiffness. It can only bounce at one speed.
You are correct. A conventional spring cannot do this. You have to abandon the spring entirely. Instead, you use a pendulum absorber.
A pendulum, like the brass weights swinging back and forth in a grandfather clock. How does that go inside a spinning car engine?
It uses the exact same physical principle as a grandfather clock, but it operates in a centrifugal field instead of a gravitational field. Instead of tuning an auxiliary mass to a constant time frequency in hertz, pendulum absorbers are cleverly designed to tune themselves to a specific order of vibration.
I am having a hard time visualizing this. Break down the physics.
In a standard gravity pendulum hanging on a wall, the natural frequency, how fast it swings back and forth, depends on two things: the constant downward pull of Earth's gravity and the fixed length of the string. Now, remove Earth's gravity from the equation. Imagine a metal mass pinned to the face of a rotating disc, like the cheek of an engine crankshaft.
Okay, so there's a heavy metal ear pinned to the side of the spinning shaft.
As the crankshaft spins faster and faster, centrifugal force acts exactly like a massive localized gravitational field, pulling the pendulum mass straight outward, radially, away from the center of rotation.
Okay, so the faster the engine spins, the stronger the artificial gravity pulling on the pendulum.
Exactly. And here's the profound mathematical connection that makes this work. The restoring force pulling that centrifugal pendulum back to center, and therefore its natural swinging frequency, is directly proportional to the rotational speed of the shaft.
Wait, let me process that. Are you saying that if the engine shaft spins twice as fast, the centrifugal gravity becomes stronger, which naturally makes the pendulum's bouncing frequency become exactly twice as fast?
Yes, it perfectly, instantaneously tracks the engine speed. By carefully choosing the geometry, specifically the length of the pendulum arm, which is the distance from its pivot pin to the center of mass of the swinging weight, you can permanently set the ratio. You can geometrically tune the pendulum so its natural frequency is exactly 4.5 times the shaft speed, no matter what the shaft speed actually
It
is.
self-tunes. As the engine revs up, the centrifugal force stiffens the pendulum exactly the right amount to keep it locked onto the 4.5 order. That is next-level engineering. You are literally using the engine's own destructive rotational energy to stiffen the absorber exactly as much as it needs to be stiffened.
It is brilliant. It's a dynamic absorber that dynamically adapts its own stiffness. It stays perfectly in tune with the disturbing torque, whether you are stuck in traffic or racing on a track.
That is genius on paper, but I have to ask about the physical reality. The source material mentioned that these mechanisms take an absolute beating in the real world.
They endure a horrific environment. The pendulum masses are usually quite small compared to the massive steel crankshaft they are attached to. To generate enough equivalent mass and counter-torque to stop a heavy engine from twisting, these tiny pendulums have to swing through fairly large arcs at incredibly high speeds.
So they are thrashing violently inside a hot, oil-filled crankcase.
Yes, and the centrifugal forces pushing them outward against their pivot pins are immense. Thousands of Gs of force. The text specifically notes a major real-world point of failure. Even a microscopic amount of physical wear on the pivot holes or the steel pins can ruin the tuning or cause the mechanism to bind up.
Right, because if the steel pin wears down by just a millimeter, the effective swinging length of the pendulum geometry changes, and suddenly your perfectly tuned 4.5 order absorber is accidentally tuned to the 4.4 order, rendering it completely useless.
Exactly. And because of the tiny, rapid vibrating motions under extreme high pressure, a specific type of damage called fretting wear is a massive problem. To survive in practice, engineers can't just drill a hole and insert a pin. They have to use specialized, ultra-hardened pins and bushings. Sometimes they abandon pins entirely and design roller-type pendulums, where the mass rolls on complex curved tracks rather than pivoting, just to distribute the intense contact loads and maintain that mathematically perfect geometry over hundreds of millions of cycles.
Okay, I want to bring up another advanced real-world application from the sources. We've talked about whirling shafts and vibrating car engines. Let's talk about a manufacturing nightmare. Let's talk about chatter and stick-slip in heavy machining.
Ah yes, tool chatter. Anyone who has spent time near a lathe knows that sound.
It's the worst sound in the world. For anyone listening who hasn't worked in a machine shop, the sources mention a specific tool called a boring bar. A boring bar is essentially a long, skinny steel pole with a sharp cutting tip on the end. You stick it deep inside a pre-drilled hole in a spinning piece of metal to widen the inside of the hole out. Because the tool has to be long and skinny to fit deep inside the hole, it is inherently very flexible. It lacks stiffness. And when that cutting tip engages the spinning metal, it screams, it vibrates violently, deafening everyone in the room, and it leaves a terrible, jagged, wavy finish on the inside of the part, ruining it.
That horrific screaming is a classic textbook example of a self-excited vibration. And it is specifically driven by a frictional phenomenon that the text refers to as stick-slip rubs.
Stick-slip, let's unpack the microscopic physics of that. What is actually happening at the cutting tip?
It all comes down to the fundamental nature of dry friction at very low relative rubbing speeds. We all intuitively know the difference between static friction and kinetic friction, even if we don't use those words. Static friction is the force required to get a stationary object to start sliding. Kinetic friction is the force required to keep it sliding once it's moving.
Right. It's way harder to put your shoulder into a heavy refrigerator to break it loose and start it moving than it is to keep it sliding across the linoleum. Static friction is higher than kinetic friction.
Exactly. Now, apply that exact principle to the microscopic cutting tip of a long, boring bar rubbing against a spinning steel workpiece. At the microscopic level, as the tool rubs against the metal, it catches. It grabs a microscopic burr. Because the relative speed is momentarily zero, static friction takes over. It sticks.
Because static friction is high.
Yes. And because the tip is physically stuck to the metal, the massive, powerful rotating workpiece drags the tip along with it, pulling it downward, bending that long, flexible, boring bar. The bar acts exactly like a giant diving board or a spring, storing up elastic strain energy as it bends.
It's winding up. It's being pulled further and further from its equilibrium position.
It winds up until the elastic restoring force in the heavily bent bar finally becomes stronger than the static friction force holding the tip to the metal. At that exact moment, the tool violently breaks free. It snaps. It transitions instantly from high static friction to lower kinetic friction, so there is very little resistance as it slides. The tool suddenly slips backward at high speed against the direction of rotation, gouging a deep wave into the metal. Then it reaches the end of its snap, stops moving relative to the metal. Static friction grabs it again, it sticks, and the entire cycle repeats.
Catch, bend, snap back. Catch, bend, snap back.
Yes. And it does this thousands of times a second, creating that horrible screeching chatter. It's not a smooth sinusoidal harmonic vibration like a tuning fork. I understand the skepticism. It sounds like a terrible idea. But engineers will actually drill a hollow cavity inside the boring bar, right behind the cutting tip. And they place a carefully sized loose mass inside it, essentially a heavy, solid slug of heavy metal, like tungsten.
It's just a loose chunk of tungsten rattling around.
It's carefully engineered rattling. This acts as a specialized type of vibration absorber called an impact damper or a friction damper. It doesn't use a spring to enforce a node like the hair clipper. It uses mass and collisions. As the boring bar starts to chatter and vibrate in that stick-slip cycle, the massive metal bar is accelerating violently back and forth. But that loose internal tungsten slug has inertia. It wants to stay still.
Okay, so as the bar snaps one way, the slug gets thrown against the inside wall of the cavity.
Exactly. It crashes into the walls of the cavity or it violently rubs against them, depending on the exact geometry. The key to the physics is that the slug moves out of phase with the main bar. Every single time the boring bar tries to snap back during the high-speed slip phase, the heavy internal slug crashes into the leading wall of the cavity.
It's acting like a counterpunch.
It is precisely a counterpunch. It interrupts the smooth snapback cycle, destroying the rhythm, and it dissipates that massive stored elastic energy. But instead of the energy going into a screaming vibration that ruins the part, the energy is dissipated as microscopic heat and localized impact noise inside the hidden cavity. It physically prevents the stick-slip cycle from building into a destructive, runaway chatter.
That is fascinating. It's exactly like putting a dead blow hammer inside the tool. A dead blow hammer has lead shot inside the head, so it doesn't bounce when you hit something. The internal mass absorbs the recoil. But there's a really specific, fascinating detail the source points out about how to design this internal cavity. You don't want the slug perfectly loose. You need to damp its movement slightly.
Right. You have to control how the slug moves to maximize the energy dissipation. You don't want it just freely bouncing. You want resistance. Now, logically, based on everything we've talked about with viscous damping, you would think that filling the cavity with a thick, heavy oil would be the best way to damp the movement of the slug and absorb the energy.
Yeah, of course. Viscous damping. Fill it with thick hydraulic fluid so the slug has to push through the goo, like a tiny shock absorber.
But the text specifically points out that in rotating boring bars, air damping is actually far preferable to oil damping.
Air over oil. That makes no sense. Oil absorbs so much more kinetic energy than air. Why would you use a weaker damper?
It has to do with the physical clearances required and the harsh reality of a rotating environment. If you fill the cavity with thick oil, you mathematically need a relatively large gap between the outer diameter of the tungsten slug and the inner wall of the cavity. You have to leave room so the thick oil can actually squeeze past the slug as it moves back and forth.
Okay, so you need a loose fit for oil, but why does a loose fit matter?
Because the boring bar might be rotating. And if it is rotating, centrifugal force comes into play. Centrifugal force is constantly throwing that internal tungsten slug hard outward, pressing it against the outer wall of the internal cavity.
Oh, I see where this is going.
If the gap around the slug is large, which is strictly required if you want to use oil damping, the heavy slug gets pushed through the oil, pins itself hard against the metal wall due to the centrifugal force, and becomes completely immobilized. The friction of it pressing against the wall is too high. It can't slide back and forth anymore.
It gets locked up. It just becomes a static, dead weight glued to the side of the cavity.
Exactly. Centrifugal lockup. And if it's locked to the wall, it can't move relative to the bar. So it can't provide that out-of-phase counterpunch. It stops damping the chatter entirely.
So how does air fix this?
With air damping, you don't need a large gap. because air is a gas. It flows much easier than thick oil. This means engineers can machine the tungsten slug to fit incredibly tight inside the cavity. We're talking clearances of just a few thousandths of an inch, a microscopic gap.
Okay, but it still gets pushed against the wall by centrifugal force, right?
It does. But because the physical clearance is so incredibly tight, the slug is mechanically constrained to stay extremely close to the center axis of rotation. The distance it can travel off-center is mathematically minimized. The tighter fit physically prevents it from moving far enough off-center to generate a locking frictional force. It guarantees that even under high rotational speeds, the slug can still slide back and forth, pumping air through that microscopic gap and doing its job of breaking up the stick-slip chatter cycle.
That is such a brilliant, non-intuitive, real-world detail. You intentionally sacrifice the mathematically superior high damping of thick oil just so you can use physically tighter manufacturing tolerances to defeat the mechanical reality of centrifugal lockup. That right there is the fundamental difference between solving an equation in a textbook and actually practicing real-world mechanical engineering.
It perfectly highlights how deeply multidisciplinary these vibration problems are. You aren't just solving a clean, isolated mass spring vibration equation. You are simultaneously fighting dry friction at the cutting tip, centrifugal force inside the tool, fluid dynamics of the damper, and tight spatial constraints, all at the exact same time.
We have covered an incredible amount of ground today. We've gone from the molecular level of metal friction to the aerodynamic whirling of airplane propellers. So what does this all mean? I want to synthesize the core takeaways from this massive stack of source material by answering the three most common questions working engineers ask when they run into these destructive vibration nightmares.
I think that's a great way to consolidate everything we've unpacked.
Question 1, how do I handle infinite complexity? I have a real-world continuous structure with distributed mass, like a custom frame. I can't solve infinite differential equations. How do I find the natural frequency?
The answer is Rayleigh's method. You bypass the impossible calculus by assuming a realistic deflection shape like a simple gravity sag and mathematically equating the maximum kinetic energy as it passes through equilibrium with the maximum strain energy at peak deflection. It allows you to find highly accurate approximations of the fundamental frequency using basic algebraic conservation of energy. And remember, the math protects you. A wrong guess structurally adds artificial stiffness, which always yields a higher calculated frequency. So you just guess a few shapes, run the simple math, and select the lowest value. It is guaranteed to be the most accurate.
Question 2, how do I stop a severe single-frequency vibration when I absolutely cannot change the speed or redesign the massive main machine?
The answer is dynamic vibration absorbers. You bolt on an auxiliary mass and spring tune precisely to the target excitation frequency. This creates infinite equivalent mass and enforces a node of absolute zero motion on the main machine. But crucially, you must mitigate the danger of the two new resonant frequencies you just created. You do this by including optimized viscous damping. You mathematically tune the spring stiffness to level the two new resonant peaks at the invariant fixed points A and B, and then you optimize the fluid damping to flatten the response curve into a safe plateau between them, preventing catastrophic destruction during spool-up.
And finally, question 3, how do I handle highly variable engine speeds where the destructive frequency is constantly scaling up and down with the RPM?
The answer is pendulum absorbers. By completely replacing a traditional constant stiffness steel spring with a centrifugal pendulum swinging on the rotor, the restoring force becomes directly proportional to the rotational speed. The centrifugal force acts as a variable gravity. This brilliant geometric trick allows the absorber to automatically scale its own natural frequency, completely neutralizing specific torsional resonance orders like the 4.5 order, regardless of whether the engine is idling at a stoplight or running flat out at redline.
It really is brilliant stuff.
It is. And if I can leave you with a final provocative thought to mull over, we spend so much time in traditional engineering trying to build structures that are incredibly massive, incredibly rigid to survive dynamic forces. We try to fight the energy. We try to overpower it with sheer stiffness.
Right. When in doubt, make the steel thicker, make the frame heavier, bolt it down harder.
But looking at the math and the elegant physical reality of dynamic absorbers, whether it's a precisely tuned pendulum swinging inside a screaming car engine or just a loose slug of tungsten rattling around inside a chattering, boring bar, the ultimate solution isn't fighting the energy. The ultimate solution is giving the energy a secondary, sacrificial system to play in.
It's like mechanical martial arts. Like judo or aikido, you don't rigidly block the punch, you grab the energy of the punch and redirect it past you.
Precisely. You redirect the chaos into a small, calculated component designed specifically to absorb it, fall out of phase with it, and safely dissipate it as heat. It really makes you wonder what other seemingly impossible engineering problems, or even human systems for that matter, could be elegantly solved by designing for fluid redirection and absorption rather than just stubbornly building a thicker wall.
Give the gremlins a different toy to play with. Let them exhaust themselves on a decoy. I absolutely love that perspective. If you got something useful out of today's episode, hit follow and drop a like. It helps grow the show and keeps the engineering knowledge flowing.